mechanics is a branch of physics dealing with the very small. It leads to what may be some very strange conclusions about the material world. At the atomic and subatomic scale, many equations of classical mechanics describing how things move at everyday sizes and speeds no longer hold. In classical mechanics, objects exist in a specific place at a specific time. But in quantum mechanics, objects instead exist in a haze of probability. It can be understood that they have a certain chance of being at point A, another chance of being at point B, and so on.
Quantum mechanics developed over many decades, beginning as a set of controversial mathematical explanations for experiments that the mathematics of classical mechanics could not explain.
Extreme quantum states. Is that particle of light like a tiny ball, flying through space, or like something smeared everywhere at once?
The answer depends on whether the bizarre laws of subatomic particles or the equations that only determine the behavior of larger objects hold more sway.
Now, for the first time, physicists have found a way to mathematically determine the degree of quantumness that anything, a particle, atom, molecule, or even a planet, exhibits.
The results suggest a way to quantify quantumness and identify the extreme quantum states of a system, which the research team calls King's and Queen's Society quantumness, which can be understood as the kings and queens of quantum. Besides enhancing our understanding of the universe, the research can be applied in quantum technologies such as gravitational wave detectors and ultra-precise measurement devices.
The heart of reality.
At the subatomic heart of reality, the strange world of quantum mechanics reigns.
According to these mind-bending rules, tiny subatomic particles, such as electrons, can be entangled in strange-looking states, meaning an electron can exist in multiple states at once. Its position around the atom or even its momentum is not fixed until it is observed.
These particles even have the ability to tunnel through seemingly impenetrable barriers.
On the other hand, classical objects obey the normal, everyday rules of our experience. Billiard balls collide, cannonballs fly in parabolic arcs, and planets orbit according to well-known physics equations. Researchers have long pondered this strange situation, where some entities in the universe can be defined in a classical way, while other entities obey probabilistic quantum laws, meaning you can only measure possible outcomes. But according to quantum mechanics, everything is quantum. As Aaron Goldberg, a physicist at the University of Toronto in Canada and lead author of the paper, told Live Science, "We see these strange things every day, doesn't?" Goldberg's point is that classical objects like billiard balls are secret quantum systems, so there is some incredibly small probability that they will tunnel through the side of the billiard table. This suggests there is a continuum with classicality at one end and quantumness at the other. Previous efforts to quantify quantumness have always considered specific quantum systems, such as those containing light particles.
And thus the results did not necessarily apply to other systems, including different particles like atoms.
Instead, Goldberg, Sanchez Soto, and their team sought a general way to identify the extremes in quantum states. According to Goldberg, we can apply this to any quantum system, like atoms, molecules, light, or even combinations of those things, using the same guiding principles. The team discovered that these quantum extremes can have at least two different types, naming some kings and others queens for their truly first-rate nature. So what exactly does it mean for something to be the most quantum?
This is where things get complicated because it is highly mathematical and extremely difficult to visualize. But Peter Cook, a physicist at the University of Sheffield in the UK, who was not involved in writing the new paper, suggested a way to grasp it. As Cook told Live Science, one of the most basic physical systems is a simple harmonic oscillator. That is, a ball on a spring moving back and forth. A quantum particle would be at the extreme of classical mechanics, it would behave like this ball and spring system.
seen at specific times based on the initial kick it received. But if the particle is quantum mechanically smeared so it has no well-defined position and is found throughout the path of the spring and ball, then it would be in one of these extreme quantum states. Despite their peculiar nature,
the results are quite useful. It is hoped it will be widely applied.
Knowing that there is a fundamental limit at which a system operates with the maximum possible quantumness is like knowing that the speed of light exists. It sets boundaries for how complex things can be analyzed. Goldberg said the most obvious applications should come from quantum metrology, where engineers try to measure physical constants and other properties with extreme precision.
For example, gravitational wave detectors need to be able to measure the distance between two mirrors to better than 1/10,000th the size of an atomic nucleus.
Using the team's principles, physicists could improve upon this impressive feat. The discovery could also aid researchers in fields such as quantum communication, information processing, and quantum computing.
There are likely many applications that physicists haven't even thought of yet.
Quantum mechanics has achieved resounding success in explaining many features of our world. All the distinctive properties of the particles that make up all forms of matter, electrons, protons, neutrons, can only be described by quantum mechanics. Quantum mechanics is also important in understanding how individual atoms combine to form substances. Quantum mechanics can allow a deep look into the underlying processes of chemistry by showing how molecules are in energetically favorable states compared to other states and how they differ. Most calculations in computational chemistry are based on quantum mechanics. Many modern technologies use devices where quantum effects play a crucial role.
Examples include lasers, transistors, electron microscopes, and nuclear magnetic resonance imaging.
Research on semiconductors led to the invention of diodes and transistors, essential electronic components in modern society. Researchers are currently exploring ways to manipulate quantum states.
One such effort is quantum cryptography, which enables secure information transmission. Further ahead is the development of quantum computers, capable of performing calculations much faster than current computers.
Another field is quantum teleportation, which could allow the transmission of quantum states across any distance in the universe. Thank you for watching the video.